Welcome to a new test and teardown video. This time it's a Wavetek model 3001, or would you say 3001 signal generator. It is from about 1984. At least this is what's printed in the manual. I will put in a picture of this unit as I got it before the cleanup, so you can see all the yellow and all the stickers and all the nasty stuff I have removed. And now look at this, how nice and beautiful and fine it looks, much more presentable for the video. So this signal generator goes from 1 megahertz all the way to 520 megahertz. It is insanely complicated and complex designed. We got 5 PLLs and all sorts of mixers and DA converters and oscillators. This is really wild. So this is the megahertz section. And the lowest you can set this to is, of course, 1. And then you can dial it down to 520 as the maximum. And that will be the kilohertz. And that is done by another system, another oscillator and PLL system. And this is, of course, another individual system. And then they are mixed together and filtered and all that kind of stuff. I think I will get into that a little bit later, but first we need to inspect this fantastic unit a little bit more. So how much is this worth today? It's really hard to tell. Last year one was sold on eBay for about $152. I got this one for free, I think a long time ago, and now I wanted to play with it and see if it works. So here at the rear, we can see the 2 different mains voltage options, either 115 or 230. So that's quite modern for a system from 1984. Got some connectivity and external reference. And a little bit of options here. We don't know exactly what is that. In here is, of course, the model. And this serial number. It's sometimes a little bit funny to see that. And look how really complex this one is designed. You'll see all these different metal boxes, and this is of course a very good way to do these things. So we got the different oscillators and PLLs and mixers and all that kind of stuff in individual metal cases, because of course it's working at a much higher frequency. So it's about 1500 and 1700 megahertz, I think, the 2 highest oscillators. And then they are mixed together into the final output, 1 to 520, and then it's amplified and all that kind of stuff. And then it's driving the output right here, and that will be the attenuator that is in here. See, it's controlled electronically using this switch. Not the cheap way to do it, but this is the best way to do it. And so all things in this unit is just made as good as they could possibly make it back then. And that will be one of the digital boards. I think this is the one that's handling the switches for all the sets. And you can see all the capacitors and filters for everything that goes in and out. And they are doing this in all the boxes as well, with filters and all that. The power supply is also quite complicated. We got a lot of different positive and negative voltages, and regulated this and regulated that. So I really hope to be able to find the checkpoints real easy. I should probably just put in a fast snip of the schematic for the power supply so you can easily see all the different regulated voltages. We got some trimmers. I think there is more than one, but there should be one for the plus minus 18, and then there's also a 7.5 that is used. This is a pre-regulated, there's a regulator somewhere right there, and this one is distributed to all the different modules, and then they have local 5-volt regulators, so it's nice and clean, and to avoid crosstalk and all sorts of things. A little switch for reset. We got some LEDs. I mean, let's see if there's anything cool to see from the bottom as well. Those little screws you see here. The idea is to avoid, see, this is a thin piece of aluminium. So to avoid, if you put this on top of something, it will bend down and create shorts. So this is to hold them up, I guess. Yeah, we also got some here. So this is, of course, also the screws to take out the modules. I think we got these, and that will be the steering for the modules. Probably they will be in a sort of a connector style, so you can just unscrew these and just pull out the modules. I think I will try and have a little look into some of the modules, most likely the high frequency oscillators and the last mixer and amplifier. I think that is the most interesting to look at, really. So let's try and see. This is of course going to be the first power up. Let's try and test this switch as well. I don't know what to expect. Mains is applied, and let's flip the switch. We got a little bit of blinkety blink, and we got output. I set this for 10 megahertz, so I've just adjusted the scope. I don't know if you're impressed, but I'm quite happy about this. So let's zoom a little bit in on what is written right there. I don't know, can you see it says 10 megahertz and a few decimals, and this is like ice cold, just cranked it on. That is really, really good. So if this is 10 megahertz, now we know this one is in lock. What happens if I put it to 11? No, this is 20. Oh, okay, so this is 10, 20, and then 11. Yeah. Haha. So what if I take the next one? Okay, back 10.0, and then this also works. So 10.1, 10.9. All this is working, and there's no glitches or nastiness. I see some glitches, but that's of course because this is a BCD switch. So we got 4 bits from this one. So when you are flipping this, tick tick tick, you will pass. See exactly between 3 and 4. You will get some more bits moving at the same time, and then that is why you see this glitch. And then from 4 to 5, see, you don't see this anymore, because then you have only 1 bit changing. No big surprise right there. And this is the accuracy. So there's something. So this is a tuning. Ah, here I can actually tune it. I don't know. It takes some. Oh, this is into the low decimals. I don't even think I have enough resolution on my on my scope here to show this. So okay, so this is CV mode. We have this. This is the oh yay. So there is some level here. This one needs a little bit of massage. See, the output on the scope is following more or less. Maybe it's gonna get better. So there is some funky things, but I think this is normal because there is a level feedback system in this one as well, and that is why it will have exactly the same level depending on frequencies. And let's try and see. Oh, so this is 90 megahertz and 0 and 9. It should not be able to give anything under 1 megahertz, but this is actually 0.9. What the heck? Look at that. Now you see a little bit of distortion, but we are now half a megahertz. And they have some problems with the mixers and all that. But there was a little bit of a margin. So this is 0.5 and all the way to 1. And of course it goes crappity crap if set to 0, because then there is nothing to work with. So we could also just see, can it go all the way up? That could be interesting. So I don't know if it's easy to see this on the scope, but this is, 100, 2, 3, 4, 500. Hello. $400 okay, so it goes. Maybe there is something with the output amplifier or something like that. I better just go and pick up my spectrum analyzer. We got some different curve. Oh, and there, at 250 we have nothing. That is interesting. So let's try and see what's going on. So this is 400 megahertz, and obviously stop frequency. Let's say 1 gigahertz. So that will be peak. So the 400 megahertz, all this is fine. 300. No, this is 500. So we have 500. So that is, oh, look at that. 400, 300. So this is the same level. So it was my scope that was interlocking with the sampling frequency. I hit exactly the sampling frequency, or a part of it, because it's sampling with 2 giga samples. So if you sample at 500, that will of course be where you should get exactly 0, I think. But anyway, that is why. So this thing is working. So this just reveals you need to think about what you're using as a measurement tool. So let's see. The specification says 520, and here you go. That is 520, and this close to maximum. Obviously, you will see the mixing components like that, but still it's quite low when you see this harmonic. I mean, look at that, more than 40 some dB below. So let's see, 530. So now we are over specifications, and I can of course continue all the way. Oh, here we go, unstable. So this is 590, 580, and we see some stuff going on. Okay, 560, and yeah, 560, and it's good. And by the way, it says here minus 10.6 dB, and I'm using a cable that is 1 meter long. So this is a 0.7 of a dB for the cable, and I have a 10 dB attenuator right here. So even that, my output is accurate, and I put this in the middle. See, if I dial this one, I will of course be able to move the output power. But I want to put this in the center. It should of course be adjusted for 0 dB right there, and then it should be accurate. So I was really close to the correct. I mean, this is really good. I'm super happy about this. So it really works. How cool is that? Let's try 250 megahertz again. See, here we go. And then we have a little bit of a harmonic. Should of course also document it's using 46 watts. We should just look a little bit at the output at, for example, 100 megahertz. So I don't know what you think about this. I'm using 100 hertz bandwidth. This way I can really filter out anything that should be or should not be going on in this area here. And yeah, my span is 1 megahertz. And here's the fun thing. If we look at the dial, the frequency dial right here, see, it says 100.000, right? So what happens if I click the first one? Tick. So one little tick on the first one should give me, see, 1 kilohertz. So now I've moved 1 kilohertz, and now you see the marker right there. I can give you 1, 2, 3, 5. So 5 kilohertz I moved. And there you have it. See, now for a fun reason, we have this ratio between the two oscillators, and now you can start to see something that is going on in here. Let's try and change this a little bit and give you, okay, yeah, let's give it 50. Let's see if it's more visible. No, then it's not visible. That is funny. So something goes on in this area here. See, now I'm back 20 kilohertz. And there you have it. Now it's visible. So you have some different filters in the different PLLs and the different oscillators and mixers and all those kinds of things that will give you those in-band results right there. So that is a little bit interesting, but it's still, I mean, if we look at the specifications, this is really low. I mean, if I take any other source, I could probably take a brand new cyclone generator to compare with. Yeah, let's try and do that. So this is 100.02. Okay, so let's compare. Now I'm ready. So this is the Wavetek generator. Now note the curve and the little in-bond spores here, and just the level of exactly what is going on. So now I pull out the cable and see this is the background level from the spectrum analyzer. So now I stick it into my cyclone generator. And there you have it. So I think my new modern cyclone generator is of course a lot better. And they have made some in-band filters that will remove all sorts of nastiness really close to the wanted, to give a very good performance right here. And here it is. So this is the little modern compact cyclone unit. I use this more or less all the time. I'm super happy about that one, really. But it's really good. Let's do a fast explainer about how this unit is designed. So here at this block diagram here, let's just focus on the top DA converter wide VCO, and then this wide VCO generates 1199 to 1718 megahertz, really high frequency, right? So the idea is the 3 megahertz setup wheels, the BCD switches, they are of course in a PLL system with the wide VCO. And the wide VCO works this way, that its DA voltage goes directly into the VCO voltage set point, but then there is on top of that a PLL to make it super accurate. This way it's of course very complex, but it's also very, very fast. So immediately when you switch around hundreds of megahertz or tens of megahertz, it actually appears immediately, and then within the next few microseconds it will its PLL will steer it back in. So that is why they have done it this way. Then there is the narrow VCO, as you see at the bottom of this picture here. And this is, of course, for fine adjustments, for some modulation and all that kind of stuff. So the narrow VCO is not doing the kilohertz. The kilohertz is also done in the wide VCO. So that is an important point. Then the final mixer unit, of course, makes the 1 to 520 megahertz. All this, the two VCOs, the wide and the narrow, and the final mixer and all that is inside one unit. This picture shows a much more detailed version of the first that I just explained about. Here we see a little bit more about the different amplifiers and the voltage controlled attenuators and all those things. We also see how the output power monitor is working. There is a closed loop with an error amplifier. We got some levels in many of those different modules, more or less all of them. You will have all sorts of little diode rectifiers and local feedback systems, so that they are holding amplitudes completely accurate and to a known fixed value throughout temperatures and frequencies and all that kind of stuff. This they also call a block diagram, but I think this is much more of a module, how the different modules they are interconnected. And today I will just open the modules shown here. I don't really want to sit here and read everything for you here. I think this is a good place to pause and then read all this text yourself. They added a lot of real good explanation about the different PLL systems and frequencies and how all this is done. And there is a pretty good reason for why they did it this way. Also feel free to download the manual and get all the deep insights about this unit. It's very, very easy to find, and they have added all sorts of really nice pictures and explainers. Like this one, for example, really helped me to figure out how it works. This explains and show phase locked loop 2. And then last, here is the explainer about this final unit just before the output amplifier, that shows how the two oscillators, they are mixed together. And of course it is full of level measurement and level feedback systems. It's just amazing. I will definitely show you this unit inside in a minute. So this is the module M9W. I guess this is not the -5 version. That's the one I have in the schematics. This is my main output. This output goes, of course, to the output amplifier. So this is 1 to 520 megahertz output, and look at that. This one is loose. And it's cracked in the solderings down there, and it has been like this for a while. I can see some really nasty dents here, and that's because they couldn't unscrew the nut, so they had to hold this one instead of just fixing the real problem. So I will of course do that. So this module here is the oscillators and mixer and output filter and all that. It's actually almost everything in one module except for all the locks and all that. But in here we got both the high and the low oscillators. Remember we talked about the kilohertz oscillators and the megahertz oscillator. So the kilohertz oscillator is one of these two. I can't really tell from looking at this because they're very high frequency, both of them. So the kilohertz one, let's just guess it's this one, I don't know. But the kilohertz oscillator is 1198 megahertz plus minus 1 kilohertz, right? Or almost 1 megahertz, right? And then the other one goes in 1 megahertz step. And that one goes from 1199 to 1718 megahertz. So those two very high frequencies, they go, let's see if we can see this, but those tiny little copper wires here goes into those two modules, and they goes into the little transformer here and this little tiny little transformer right there. It's real difficult because we don't have any light in here. And you also see 4 little diodes in here, so that will be the little mixer. And out is of course the difference between those two frequencies, and that will be 1 to 520 megahertz. And the cool thing about doing it this way, with using two really high oscillators, that means the difference and the sum. So now you see the sum is very high, and that means really easy to filter away. And now you have only the difference in a very good and filtered way, and then you amplify and filter it here, and there you have your output. So yeah, that is really beautiful, I must say. I kind of like the way that they have tried to isolate everything here. It's almost touching down there, so better lift it a little bit like that, and shield it around the different components. And I mean, I'm really impressed with the building style and quality, and also how compact it is. It's really compact. Can you imagine manufacturing this in a high volume? I mean, what? A lot of hours went into this. I should of course show a block diagram of this unit, so it's much easier to understand exactly what is going on. And I should also show the full schematic with all the details shown about this unit, so you can enjoy all the fantastic things they did. I must say I am impressed. So now it's repaired. I just solder it up here, real easy. It takes only a few seconds to solder stuff like this. But I'm also cheating. I'm using a Metcal, and if you don't know, oh, let me clean this. Metcal, yeah, man, you just get the most impressive amount of heat, and it's not really hot. It's just able to solder on anything, no matter how thick or difficult it looks. Yeah, I can just solder it all the time. So now I think this is repaired and good and stable again. So here is the output power amplifier. And I think I'll be able to open this one quite easy by just going in here, right? So now we're inside the output amplifier unit. I added a little bit explainer here so we can easier see what's going on. I really like this design and the way that this is, of course, this takes a lot of hand work to solve this. We got a little bit of inductor resistor filter and parts that's nicely shielded. Look at that. And then we go into the transistor amplifiers right there. And of course everything is with inductors and capacitors and everything as well. And then we go through here. Another little transistor amplifier and another one. And in here we got 2 more transistor amplifiers. And then look at that little bendy thingy here. So that is of course a little frequency compensation thing. And we got some diodes because they are of course measuring. Yeah, that is this system here. So they're measuring the output power, and this output power goes back into a system that is right here. All those transistors, and this is a little differential amplifier instead of having an op amp or anything like that. And then it knows what is the output power and can compensate for this somewhere else. But it's really beautiful. And think about this. Maybe this is brass or something like that, and then they added some tin on it, and then all the transistors, they go into holes like this and they're soldered on the other side. This is really good for thermal, so good thermal design. And this is probably Teflon, and you see those 4 little holes here with little springs. The idea is you stick in your components and they actually stay there, and then you can build your circuit, and then when you're done you solder it and then you finalize it, and you can of course also access the signals on the other side. So yeah, a pretty good design method, and I bet all the units, they will be designed like this. So this unit here is called the M10W. And note, there is no extra numbers or letters or anything like that. So this is the early version. The schematic I want to show you from the manual I got is a much later version. And that one is with some op amps and a little relay and all that. So it's quite a big difference from that one to the one I got here. So now I'm playing with the different modulations. It's a lot of fun to see what it can do and how it's looking in the different modes and all that. But anyway, I don't think I want to make this video a lot longer. I'm just really happy that it works, and it just made my day. So thank you very much for watching. I hope to see you soon again. Bye bye.